Hey guys, today we're going to be talking about dynamics of rotational motion by me, Jan Philippe Ang. So getting right into it, we have our problem. At 12 kilogram box resting on a horizontal frictionless surface is attached to a 5 kilogram weight by a thin light wire that passes over a frictionless pulley. The pulley has the shape of a uniform solid disc of mass 2.10 kilograms and a diameter of 5.560 meters. After the system is released, find A, the tension of the pulley on the wire on both sides of the pulley, the acceleration of the box, and C, the horizontal and vertical components of the force, right? So we have our given mass 1 equals 12 kilograms, mass 2, 5 kilograms, mass of the pulley 2.10 kilograms, and a radius of 0.560 meters. Our required is A, tension of wire on both sides, B, acceleration of box, and the force components of axle on the pulley. So that's our given and our required. So this is the free body diagram. This is how it looks like, 1, 2, and the pulley. So first thing we need to do is we set up our equations using Newton's second law of motion. So you can see that in A, T1 equals M1A, and then T2 equals M2G minus M2A. So then the next thing I did was find the acceleration. So we have the total force, and then we have the total mass. So if we add that all up, oh, also note that I used 1/2 m for the pulley because of its solid cylindrical shape. That's 1/2 m, which will give you 2.7 meters per second squared. And then if you look up there, that is when we plug in the acceleration to look for T2 and T1. So now we already have our tensions and we have our acceleration of the box. So then we have to look for the force components. So on the X, we only have the tension, so we just plug in 32.4 newtons. But for Y, we have to add the weight of the pulley. So it's 35.5 plus 2.10 times 9.8, which will give you a total of 56.08 newtons that is exerted on the pulley itself by the axle. For our second problem, we have this photo. The mechanism shown is used to raise a crate of supplies from a ship's hold. The crate has a total mass of 53 kilograms. A rope is wrapped around a wooden cylinder that turns on a metal axle. The cylinder has a radius of 0.24 meters and moment of inertia I equals 2.9 kilogram meters squared about the axle. The crate is suspended from the free end of the rope. One end of the axle pivots on frictionless bearings. A crank handle is attached to the other end. When the crank is turned, the end of the handle rotates about the axle in a vertical circle of radius 0.12 meters. The cylinder turns and the crate is raised. What magnitude of force applied tangentially to the rotating crank is required to raise the crate with an acceleration of 1.40 meters per second squared? So you could ignore everything that wasn't mentioned. So you have 53 kilograms, 0.24 meters, 2.9 kilogram meters squared, and 0.12 meters. So we already have the moment of inertia, we have the two radii, and one mass. So required, we only need the force needed to create a lift at acceleration equals 1.40 meters per second squared. So this is the free body diagram, and we start off with creating a force equals mass times acceleration equation. So we look for the tension, and it's pretty simple, pretty straightforward. So we'll have 593.6 newtons. Then we have to convert that into torque, because that's the thing that we're trying to overcome. So we multiply that tension with the radius 0.24, which will give us 142.46 newton meters in torque. So then we convert the linear acceleration to rotational acceleration, which is our alpha. So we have 1.4 over 0.24, which is your r. So that'll give you 5.83 radians per second squared. And then we convert that to torque again. So we multiply that by 2.9, which will give you a second torque of 16.907 newton meters. So we add the two torques, which is 159.38 newton meters, and we divide that by the radius that we are applying the force at. So once you do that, you will get a force equal to 1,328.06 newtons of force needed to lift the crate So for our third and final problem, we have this shown here on the screen. A small block with a mass 0.200 kilograms is attached to a string passing through a hole in a frictionless horizontal surface. The block is originally revolving in a circle with a radius of 0.790 meters about the hole with a tangential speed of 3.70 meters per second. The string is then pulled slowly from below, shortening the radius of the circle in which the block revolves. The breaking strength of the string is 31.0 newtons. What is the radius of the circle when the string breaks? So here we have our diagram, and we're gonna go into our given, which is just 0.2 kilograms, radius of 0.790 meters, and a velocity of 3.70 meters per second. So for our required, we are going to have R when tension equals 31 meters, because that is when it breaks rather. So, solution. First thing to note is angular momentum is constant because there is no torque. So we use L equals mvr, and we can convert that so that we have L over mv. So then we get our tension, which is mv squared over r, and you can convert that to m over r times L over, that should be mr squared, sorry. And then you get the final formula of L squared over m r cubed. So then we calculate for our angular momentum. So you just plug everything in, 0.2, 3.70, and 0.790, which will give you 0.585 kilograms per meter squared. So then we have 31. We plug that in as our braking force, and then you equal it to L squared, which is your momentum, and then you have to isolate R cubed. So we get cube root of 0.585 squared over 0.2 times 31, and that'll equal a string length of 0.3808 meters before it breaks. Okay guys, thanks for watching, and that'll be all. Till next time.